Measuring water flow in a closed, pressurized pipe is straightforward, but tracking discharge in an open river requires a different approach. We use notches and weirs, the essential instruments for quantifying flow in open channels. This matrix compares the two. A notch is a precision plate for laboratory tanks. A weir is a massive concrete structure in actual rivers. The synthesis insight shows that despite scale differences, governing equations for both derive from the same foundation, Bernoulli's principle. This diagram displays a weir in action. The top edge is the crest. Water passing over forms an upper and lower nappe. Notice the ventilation zone underneath. If not aerated, a vacuum pulls the water down, artificially increasing discharge. Always assume free ventilation. Pinning down this anatomy and verifying your baseline assumptions is the first step. From here, we can start applying the exact discharge formulas. This graphic breaks down the rectangular geometry. On the left, we have a large rectangular orifice. As the top boundary of water, H1, approaches 0, the flow becomes a standard rectangular weir, shown on the right. Look at the base integration formula. For any rectangular flow geometry, the cross-sectional area is proportional to the head, h, and the velocity is proportional to the square root of h. Multiply them together, and your discharge, Q, will always integrate to h to the power of 3/2. Now compare that to this triangular cross-section, or V-notch. Because the walls angle inward, as the water level drops, the flow area decreases quadratically. This makes V-notches highly sensitive and extremely accurate for measuring very low discharge rates. The yellow box shows a crucial APPSC exam shortcut. For a standard 90-degree right-angled V-notch with a coefficient of discharge at 0.6, the entire formula collapses down to a single constant. Q equals 1.417 times h to the 5/2 power. When you read a weir numerical, your very first step is checking the shape. That tells you if you're working with a 3/2 power for rectangles or a 5/2 power for triangles. This plan view illustrates real-world flow separation. A suppressed weir matches the exact width of the channel, keeping the flow parallel. But if the weir is contracted, meaning it's narrower than the channel, the water is forced to pinch inward at the edges, reducing efficiency. To account for this mathematically, we use the Francis formula morph. For every n contraction present, you must deduct 0.1 times the head from your Bose length to find the true effective length. This brings us to a hybrid geometry, the trapezoidal weir. As the cross-section displays, it is essentially a rectangular weir flanked by two triangular V-notches. Let's focus on the deep dive text for a specific variation called the Cipolletti weir. It is built with a precise side slope of 1 horizontal to 4 vertical. This specific angle increases the flow area at the edges, which compensates for the volume loss to end contractions. So if an exam problem asks you to calculate discharge for a Cipolletti weir, do you apply the Francis correction? The answer is no. You simply use the standard rectangular formula. Spotting the word Cipolletti in a word problem is a free pass. It allows you to skip the tedious subtraction and run your numbers straight through the rectangular baseline. This crust width matrix tracks how flow behaves over different barrier types. We move from fragile, sharp-crusted plates used for precise lab measurements through an intermediate narrow-crusted state over to robust, broad-crusted concrete dams. This deep dive diagram focuses on the broad-crusted weir. Because the crust is so wide, the pressure profile shifts. As fluid enters the broad crust, its velocity increases, which causes the water depth to drop from capital H down to lowercase h. The exam questions often ask for the condition of maximum discharge. If we differentiate the discharge equation with respect to depth and solve for the peak, setting dq over the h to 0, the math reveals that flow maximizes when the crest depth h is exactly 2/3 of the total head, h. Plugging this limit into the equation yields the constant 1.705. This taxonomy chart shows what happens when tailwater rises above the crest. For submerged or drowned flow, the problem splits in two. You calculate the top layer of water as a standard free weir and the bottom layer as a submerged orifice. Locking down the 2/3 broad crest limit and the submerged split math technique protects you against the most difficult curveballs on the test. There is one final variable to account for: velocity of approach. If the river is already moving rapidly before it hits the weir, that water is carrying extra kinetic energy. To balance the energy equation, this approaching velocity translates into an extra kinetic head variable. You add this directly on top of your standard fluid depth inside the integration limits, which ultimately increases your final calculated discharge. This sheet consolidates all the high-yield diagnostic frameworks we've covered. Take a screenshot now. This is your core reference. We have core proportionalities top left and precise constants top right. Below, we map the Francis contraction deduction, approach velocity addition, rounding out with the Cipolleti shortcut. By committing these specific constants and corrections to memory, you possess the analytical framework needed to solve any APPSC AEE Weir problem with precision.